So picking up, Petra, from where we left off, and yeah, they've gotten tougher, okay? Here's what we said. If there is a collision, my strategy is still conservation of momentum. The sum of all the momentum before equals the sum of all the momentum final. That hadn't changed from physics 11, to be quite honest. And then we still asked, before the collision, what's moving? Mass 1, mass 2, or both, stuck together or separate. After the collision, what's moving? Mass 1, mass 2, or both, stuck together or separate. That gave us here, but we said as soon as we see angles, or norths of souths, or easts of wests, as soon as we see directions, now our strategy changes. We DULP, we draw a little picture. What I said was draw the momentum as an arrow, as a vector arrow, magnitude and direction of momentum 1 initial, mass times velocity, and Michael, we found sometimes we could even do it in our heads without a calculator. Draw the momentum final of mass 1, momentum 1 final, momentum 2 final, and we said, how are you going to add those two together? Well, you can draw them tip to tail. See, I don't know the final momentum of object 2, but I do know that when I add them together, I'm supposed to get dead horizontal 16, which tells me how to draw the triangle. Then we brought out the cosine law, but the cosine law only allowed us to find the momentum. It wanted us to find the velocity. We said to find the velocity, divide by the mass. Oh, that actually gave you the speed. To find the velocity, which was the directional component, do sine law. And then we paused. Because there was, I think, a part B to this question. Was there not, Cliff? What was part B asking?
Find the amount of kinetic energy lost in terms of...
Okay. Find the kinetic energy loss. I think what I'm going to do first is find the kinetic energy initial. Then I'll find the kinetic energy final. And if I subtract bigger minus smaller, hopefully that's going to tell me what was lost. And that would have gone into heat and sound and deforming the objects if they were flexible metal. I don't know what it went into, but some of it was lost. So kinetic energy initial. Before the collision, how many masses were moving? 1 or 2 or both? Sorry, 1 or 2, I guess both and 2. 1 or 2, sorry, mass 1, mass 2, or both of them before the collision. Okay, so it's going to be a half m1 v1 initial squared. It's going to be 0.5. How big was mass 1? I got to go back to my picture. 2. And my initial was 8 squared. You know what, Michael? I don't even think I need a calculator for this one either, because the half and the 2 conveniently will cancel. It's just 8 squared, which is what, my friend? 64. Apparently, we had 64 joules of kinetic energy before the collision. Wham, they collide. The final kinetic energy, both of them are moving. Now, the nice thing, though, Kelly, since energy is a scalar, I don't care about the thetas, the what of whats. I just know it's going to be a half mass 1 v1 final squared plus a half mass 2 v2 final squared. It's going to be 0.5. Mass 1 was 2. The final speed was 6.7 squared plus 0.5. Mass 2 was 10. And somewhere I found its final speed. Oh, yeah, 0.364 squared. Right? Change colors, Mr. Dueck. I think the kinetic energy loss is going to be how much you started minus how much you ended up with. It's going to be 64 joules. Take away, you know what? I wrote out the equation, but I didn't actually crunch the number here. I'm not sure I can do this one in my head quite as conveniently. 0.5 times 2 times 6.7 squared plus 0.5 times 10 times 0.364 squared. Do you get 45.55 joules of energy after, of kinetic energy after the collision? Is that right? Don't be consistent in your colors, Mr. D. 45.55. So I guess I lost 18.4 joules of kinetic energy. Mr. Dueck? Yes, Elijah. You said energy is conserved. How could you have lost that? Yeah. Total energy is conserved. Kinetic energy, which is a subgroup of energy, is not. That, in fact, every time you come to a stop in a car, you've lost kinetic energy. It's been transformed into other stuff. Okay? So 18.4 joules of energy must have gone into heat, sound, deforming the metal, and probably some other, air resistance, other forms of energy loss. Example 5. A metal disc explodes, boom, into 3 pieces, which fly off on the same geometric plane. What that's saying is they fly off on a flat surface because we don't want to go 3-dimensional. We're just handling 2-dimensional right now. The first piece has a mass of 2.4. And it flies off north at 10 meters per second. The second piece has a mass of 2.0, and it flies east at 12.5. What is the speed and direction of the third piece, which has a mass of 1.4 kilograms? Is this a collision? No. Is this an explosion? Is this a jeune? You know what this is a job for? You know what this is a job for? Conservation of energy. I'm going to start out the same way. I'm going to start out by writing, okay, the sum before the explosion, what's moving? Mass 1, mass 2, or mass 3? It's a trick question. None. Oh. So before the explosion, what's my total momentum? None. 0. You know what that means? After the explosion, what's my total momentum? Still 0. Okay. So I'm going to start out like this. After the explosion, what's moving? Mass 1, mass 2, or mass 3? All of them. Yes? Stuck together or separate? And we said from now on, pause. Now we double check. Is this question going to involve angles and trigs? Is there a theta? Is there a north of south, east of west, or other directions? Yeah? Then you know what? We better dulp. And in fact, since they're using compass directions, I'm going to go north, east, south, west. Somewhere on this question, I'm going to draw compass rose. You're not going to fool me. What does the final momentum of object 1 look like? First of all, what direction? North? How big? Mass times velocity. 24. Plus? What direction does the second piece's momentum point in? East. How big?
25.
Plus. Did they give me any info about the third momentum? Yeah. First of all, I pointed at west instead of east. I told you how often I do that. It drives me crazy. I did just catch myself as you raised your hand. No, it's mass times velocity. It's 25, mister. By the way, Nate did another common mistake. Kids want to say velocity is conserved. No, momentum is, but it has to be mass times velocity for it to work, because it's momentum. Did they give me any information about the third momentum. The third piece is momentum. Do you see anything in there? Then you know what? I'll put a question mark there, just to let myself know I looked for it, didn't see it. But they told me this question has one key difference from the previous couple that we've looked at. I know what these add to. What do they add to? Now, how the heck can that happen? Well, how will I add these three vectors together? I think I'll draw them how? Tip to tail, tip to tail. It's going to look like this. $24, yoink, 25. How can I show that this adds to 0? I have to end up back where I started from. I have to go, that's momentum of object 3 final. And conveniently, this one here has a right angle, which means no need, Harjote, for a cosine law. No need for a sine law. I can use good old Pythagoras and SOHCAHTOA. So let's see. It's going to be momentum 3 final squared equals 24 squared plus 25 squared. 24 squared plus 25 squared equals square root. 34.6554. Good hands, Pete. 34.6554. Yes? Momentum of object 3 final equals 34.655. That's not what they wanted me to find. They wanted me to find the speed. If I know the momentum, how the heck can I find the speed? Divide by the mass. Please, did they tell me the mass of the third piece? I hope they did. Oh, okay. So I'll call that V3 is going to be 34.655 divided by 1.4. Divided by 1.4. Do you get 24.8? If I now I'll go to 3 sig figs because it's kind of my final answer. 24.8. Oh, problem. Kelly, that's the speed, but this question didn't say find the speed. Kelly, this question said, what is the speed and direction? Okay, now I got to do a little trig here, but at least it's SOHCAHTOA trig. By the way, I always put theta where my vector starts, which in this case is here. And I'm pretty sure to draw it, I would go like that. It's going to be what of what? North of south, east of west? What of what? South of west or west of south? West of south, Pete, would be this. Start out going south, go west of south, it'd be that angle. Is that the one that I have? So not west of south, what is it, my friend? South of west. Let's see, does that make sense? South of west means go west, go south of, oh yeah, that works. That mirrors that particular picture there. So I'll even fill that in right now. It's going to be south of west. Now I just got to figure out how big. Oh, thankfully it's straight SOHCAHTOA. That 24, opposite, adjacent, or hypotenuse? Opposite. That 25, adjacent. By the way, the 24 and the 25 are almost identical. This is almost isosceles, not quite. It's going to be really close to 45 degrees. It's going to be like either 44 point something or 46 point something or 45 point something. Which trig function can I use? tan theta equals opposite over adjacent, running out of room, but this will work. Opposite over adjacent. Whoop. I get 40, oh, I was close, 43.8 degrees. I knew it was going to be close to 45. I like this question, I like this question, I like this question, I like this. There's going to be an explosion on your test. The reason we can handle, because I like this in that we're actually adding 3 vectors, which we've barely ever done, but the reason we can is we know the answer has to be 0, which will be the case in any explosion. Example 6. There's a word after the word collides. Begins with the letter O. What word do you see there? After the word collides, begins with the letter O. I need to give you a vocabulary word. What word do you see there? Okay, obliquely. That's a fancy word for at an angle. In other words, I have to let you know, Peter, look up, that it wasn't a straight head-on collision, that they ricocheted off each other. Now, the diagram does that too, but I wanted to sneak this word in because sometimes you'll see that on your big momentum review or in the homework. They'll use the word obliquely. Obliquely means, yeah, they banked off each other. They glanced off each other. It was not head-on. Is there a collision? Yeah? Are they talking about force and time and impulse at all? Then you know what this is a job for. Conservation of momentum. How am I going to start? The sum of all the momentum before the collision equals the sum of all the momentum after the collision. That'll get you 1 mark, probably. Before the collision, what's moving? Mass A, mass B, or both? Momentum of A initial. Wham! They collide. After the collision, what's moving? Mass A, mass B, or both? Both. Stuck together or separate? Momentum A final. Momentum B final. Am I dulping, or can I just let to the right be positive and to the left be negative and just divide and solve? I think I have to go with vector math here. Yes? You know what? I'm going to draw a little compass rose over here because apparently even when I draw it, I still get east and west mixed up, but I better draw it to at least catch it. I guess the initial momentum of object A looks like that. And it's mass times velocity. What is mass times velocity for object A before the collision? 4? Wham! They collide. Looks like mass A goes off this way, and this looks like it's the mystery momentum. I'll call it momentum of A final, because I can't put a number on there. And it looks like mass B goes down that way with apparently a 29-degree angle there. How big is the momentum of object B? Also a mass of 5 times 0.6. 3. How will I add these 2 vectors together? Draw them. Now, the nice thing is I know what they add to. This plus this has to add to exactly horizontal, which means if I draw the vector diagram, it's going to look like this. If I draw the vector diagram, it's going to look like this. Mystery vector, which I don't know. But I know to stop drawing B exactly right about there. Because I know that these are supposed to add to 4. They told me that this was 29 degrees, which I think if I use that clever Z trick, alternate interior angles, I think that that's the same angle. That's also going to be 29 degrees, yes? Come on. So I think I can say that this SOHCAHTOA, right angle triangle? No. Sine law? Ain't no pair. I got side angle side. This is a job for the cosine law. What's the cosine law? It's going to say this. The missing side squared equals side 1 squared plus side 2 squared minus 2 side 1 side 2 cos angle between them. Running out of room here. Four squared plus 3 squared minus 2 times 4 times 3 cos 29. What? Oh, I thought somebody had said don't forget something. Is momentum 4.009? What do I have to remember to do? Square root. Square root of 4 is 2, so the square root of really close to 4 should be really close to 2. I'll go 2.0023. Momentum of 3 final equals 2.0023. That's not what they asked me to find. I found the final momentum. What did they want me to find? The final what? Velocity. If I know the... Oh, divide by the mass? Okay. So velocity of object 3 final is going to be 2.0023. Is that right, Mr. Dueck? 2.0023. Yeah, that works. Divided by 5. I get a speed of, 0.40 if I go to 2 or 3 sig figs. Almost exactly, but not quite 0.4. At, because they did say direction as well, yes? Which angle would I use to find the direction? There's 2 angles inside the triangle, more specific.
One between 4 and
The bottom left one? So,
yeah.
where it starts from? There's my theta. Can I use SOHCAHTOA? Could I say this is like cosine? No, because there's no hypotenuse here necessarily. There's no right angle here. So I'm going to have to use the sine law. Sheesh. I'm going to have to fit the sine law in right here. It's going to be the sine of 29 divided by 2.0023, what's across from it, equals the sine of theta divided by what's across from it, 3. I think to get the sine theta by itself, I would times by 3. And then to get the theta by itself, how to get rid of a sine? Shift sine, I hope. So it's going to be 3 sine 29 divided by 2.0023. Shift sine? Nope, wrong button. please? 46.6 degrees. Anybody else? What of what? North of south, east of west? What of what?
North of east.
North of east. And I read a little note here, just a reminder. Kinetic energy is only conserved in that magic term, perfectly elastic collision. Remember last day we gave you the terms inelastic sticks together, elastic bounces apart, elastic rubber band, rubber bounces, bounce apart. And then we have this magical perfectly elastic where not only do they bounce apart, but they bounced apart at a 90-degree angle, you had identical masses, and kinetic energy was conserved. Let's do 7. We may pause here, we'll see. A 10-kilogram curling stone, ooh, curling, very little friction, is sliding along the ice when it hits a stationary 18-kilogram bucket of sand, also no friction. After the collision, the curling stone's velocity is 3 meters per second east, and the bucket has a velocity of 2.3 meters per second at 43 degrees south of east. What was the initial velocity, magnitude, and direction of the curling stone before the collision? Ooh. Ooh. Well, hey, race, is there a collision? Well, then I'm going to probably go like this. And I'm going to go north, whoop, let's try that again, north, east, south, west. Wow, I'm suddenly yawning. Wake up, Mr. Dueck. I'll have to yell at myself. Mickey, before the collision, what's moving? The stone, the bucket, or both? Okay, so that's going to be momentum, I'll call it S for stone initial. Bam! They collide. Mickey, after the collision, what's moving? The stone, the bucket, or both? Stuck together or separate? Momentum, stone, final, plus momentum, bucket, final. Mickey, is this question giving me directions and angles and stuff? Then I better gulp. If not, I could just let to the right be positive, to the left be negative, be consistent, and divide, and good to go. Okay. Gulp. Do I know the direction or magnitude or momentum of the stone initially? Do I know how the stone was traveling before the collision? I don't? Do I know the final velocity of the stone? Final momentum of the stone. Due east? Yoink. How big is that line? What's the magnitude of that vector arrow? (30) mass times velocity, yes? Plus and the bucket has a velocity of 2.3 meters. The bucket has a velocity of 2.3 meters per second at what, Ashley? South of what? South of what? One more time. South of what? Let's draw a dotted line to the east. Ashley, what of east? Go down south from east, yes? I'm reviewing how we found these angles, right? You know what? That's going to be the direction, with an angle of 43 degrees. How big?
41.4.
Whatever 18 times 2.3 is, what'd you say?
41.4.
41.4. Okay. I only have two vectors. How do I add them together? Stop yawning, Michael. You're making me do it. How do I add them together? Draw them tip to tail. Okay, so my vector diagram is going to look as follows. The 41.4 is going to be at an angle downwards and slightly longer than the 30. 41.4. Can you see, Manisha? I'm pretty sure the resultant is that there, which is our momentum of the stone initial, our mystery momentum. Problem, I don't have any angles in here yet. Wait. How big is that angle right there, folks? How big is this angle right here? 43. How big is that angle right there then?
137.
How'd you get 137? You're right.
Minus from 180.
Since they form a straight line, the fancy word, we call those supplementary angles. 137 degrees. SOHCAHTOA? No. Cosine law. How much room do I have here? I really need to retake. Oh, not much. Okay. You know what? I'm going to go yoink because we need the room. And I'll have to retype this lesson with more room. What's the cosine law say? I think the cosine law says mystery side squared equals side squared plus other side squared minus 2 side 1 side 2 cosine of the angle between them, 137. Going to be 30 squared plus 41.4 squared minus 2 times 30 times 41.4 times the cosine of 137. That didn't feel right. That still didn't feel right. Cos 30, okay, 30 squared plus 41. Minus 2 times 30 times 41.4. Oh, okay, I think that's right. Is the momentum of object 3 4,000? Sorry, is the velocity of object 3 4,300? Sorry? Square root. I'll even write it down, 4430, 4431. I'll square root my more accurate value. 66.563. Of course, they didn't want me to find the momentum. What did they want me to find? How can I find V? Oh. The velocity of the stone initial is going to be the square root. Sorry, not the square root, Mr. Dueck. It's going to be 6.563 divided by for some reason I started calling this momentum of object 3. What I really should have called this was momentum of object S, the stone, right? That was my earlier notation. Oh, it looks like a 5. I'm kind of regretting that now. Sorry, what, 10? Michael, I don't think I need a calculator to divide by 10. Oh, you are ever so clever. For those of you who simply can't stand that. So 6.66 units, velocity. Meters per second. Except that's not a velocity, that's a speed. Look up. Doink, now I made it a velocity. Doink, now I made it a velocity. At what? First of all, north of south, east of west? What of what? We're talking about there, I think, where the vector originates. South of, start out going east to the right, go south of that, down from, yeah, south of east. How big is angle theta? This is a job for the sine law. Sine theta over what's across from it, 41.4 equals the sine of 137 over what's across from it, which is the momentum of the stone initial, which was 66.563. 41.4 times the sine of 137 divided by 66.563. What the? Oh! Inverse sine of that. And I get 25.1 degrees. Humbly I suggest to you, holy schmole, that's a lot of work. Does your lesson have homework attached? Well, that's a little odd. Give me a second here. So, what's your homework then? From the ultimate momentum review. This is what you can work on. Eventually you'll do every question on this review, but here are some to get you started. These will be ones that involve angles and weird stuff. You can do number 1. $14, $16, $18, $22, $26, $33, $34, $37, nasty. 45, also nasty. 47. 47?
No, I'm just saying the last couple.
37 and 45 are fairly nasty. 47, it's jumping off of a life raft. That's actually an explosion. It's a very slow explosion. But if you're standing on a life raft, your momentum is 0. Afterwards, if you jump, your momentum is 0. Give me 1 second, Cliff.